I was trying to keep track on how far you guys are going. And I think in a video she posted last week, I think she always puts the subtitle in the front of the whole chapter. So here you can see she actually puts a hollow alkyne in lecture 9, part 1. And then I think last week she ended up with, just in the lecture, she ended up with some stereochemistry, which means tomorrow you're going to get started with the real tough chemistry. So that's where, when you see the words hollow alkyne, that's actually where things start. And on this page, which is the page that I'm showing here, is actually the first mechanism of the whole 118 series. In your midterm, there's also a mechanism question, but since you are open books, I think it shouldn't be that hard. Just to let you guys know, this is where you should start to pay attention and start to count how many mechanisms you have learned. The notes that I'm sending for week 6, including some parts of the mechanism that she's going to talk about, probably in tomorrow or the day after tomorrow. But you will finish the 4 mechanisms in the notes that I sent you. So I will skip that part today, and we are still going to follow what we are supposed to learn in discussion manual first. And if I have the rest of the time, after we did some practice on discussion menu, I'll go back to the notes and talk about what is our expectation from you guys. Last week, we talked about IR, which is infrared spectroscopy, and we did some exercise on that. I always like to use the example of birds in a room to describe IR and NMR spectrum. If you're using IR, you are blind, which, as you see here, this person actually cannot see anything. You may be able to hear the birds is beeping in the room, but you won't be able to see where the birds are, what's the color of the birds, and how many birds there are. You may be able to tell there are different birds because they sound differently, but that's just a guess. You are not 100% sure about it. So if we're talking about chemistry here, so if you're using IR spectrum, so you know some type of functional group. There are only a certain type of functional group. It's like the only certain type of birds that you can tell the difference from their sounds. Won't be able to know the number or the precision, which means you don't know if this functional group is next to the other. So what we are learning today is NMR, which means you are not blind anymore. Actually, in the next 3 weeks, discussion 6 to 8, so you are not blind. You can see everything in the room. Maybe there is a cat. See, there's a cat hiding in the corner, but the cat wasn't really make a sound. So you were not able to find that cat in the corner when you were using IR, but you will be able to see the cat when you are using NMR. So NMR is you will be able to see functional group, and you can have a guess on the number of functional group position. You will be able to get the information about that. Background information. I'm just going to highlight some of the information here. So the things that I didn't highlight, you just need to understand it. So first thing is magnets, because we all know moving electrons is going to make magnets. In this case, even is a proton. So because we know there are electrons in the proton. So when proton is moving, it's going to generate a small magnet. Imagine that the magnet of each proton is going to pointing at a certain direction, because electrons just moving in the ways they want. You don't know, but they are going to form an equilibrium. So so this is when they are free. So when they are free, there are no other forces or no other magnets around the proton that we're talking about, which means the proton in your sample. They're going to behave as it is. So they are all pointing at each different directions. But when there is a B naught, so magnetic field B naught, when there is a B naught applying to the sample, you're forcing all of different direction protons to pointing at either parallel or anti-parallel. If you have a small magnet, N and S, but if you are putting the small magnet in the B naught, is gonna to follow what the B naught is moving. But some of the proton, for whatever reason, that it's gonna to behave totally different, behave like this. It's more likely to be, I have another finger. So this is my finger. I'm using my finger to point at the small magnets to force it go against the magnets that I have applied to those protons. So anti-parallel is going to have a higher energy. There is one important concept that you need to know. Not all the atoms or protons, well, including carbon and other, so proton, carbon, nitrogen, fluoro, silica. So not all of them are magnets active. They are all odd number, right? So only if there one more electron is not parallel. So we all know electrons can pair into pairs. Only if there is extra one more electrons that cannot be paired into those pairs, and there's nothing that can cancel out the small magnets formed by this extra one, that we can see that. We just talk about electrons under the B naught is going to behave differently, either alpha or beta. And then we also know that there is one energy state is going to be higher because you force them to go against, so like this. So you force them to go against the direction of your B naught. So this is going to be a higher energy. So under the same circumstance, if I'm going to increase the B naught, so if I have a large B naught, then this gap, the energy gap between alpha and beta energy state is going to increase. So if I increase B naught, this energy gap is delta E is going to increase. So that's chemical shift and TMS. So when we are trying to compare different kind of electrons in NMR machine, we need to have a standard, and that standard is TMS. Also because those small magnets of each proton is very, very tiny. So we need to use parts per million. So that's the equation. We are not going to ask you to do any calculations about that. The only reason we want you to know this equation is all of the peak that we are using in NMR spectrum is some number that's good enough for us to see the difference. Otherwise, they are all something in the magnet of 10 to the minus 6 something, and we are not going to see that. We magnify all of them, all of the signal that we detected from the NMR machine by a certain number, and then we just going to use ppm. The reason that we choose this one as an example is because this one is really stable. 3 hydrogen on each carbon, and then there's 3 times 4 equals 12 hydrogen, which means this peak is going to be really strong because I have 12 hydrogen of that. And later in our discussion, we're going to talk about what is chemical equivalence. And just for your information now, all those 12 peak hydrogen are in chemical equivalence, which means this peak is going to be really sharp and clear. Another reason of choosing TMS as standard, so we just manually decide this is our standard of 0. The hydrogen peak from TMS is a standard 0 in both proton and carbon NMR. So you're going to see carbon NMR in 118B. And we just manually set the range of proton NMR to be from 0 to 10, carbon NMR from 0 to 200. So shielded and deshielded. And then my proton was pointing in this direction previously, okay? Of course, since I need to compare, so I'm going to draw the same proton. So now I manually applied the same B naught in a field. My proton would want to form something like that, right? If I have a lot of electrons around me, what would happen? Although I'm applying the same B naught, you can think about you have a lot of the friends next to you. It will be harder for the B naught to force you go to the direction. If you want to see how would that change on our diagram, that would be when you are deshielded, we easily force you to go to B naught. So that's where the deshielded. And when you are shielded, it's harder for the B naught to force you to point into the same direction of that. That's the difference between shield and D-shielded. They told you up-field signals are shielded and have relatively high electron densities around observed atom nuclei. Starting from shielded and de-shielded, we are going to differentiate different functional groups. You are also going to see something like oxygen, nitrogen, halogens. So they are very electronegative. That is going to steal some of your electrons away. Especially we're talking about protons. So when you are bonded to something very electronegative, your electrons has been stolen away by those atoms, which means you are not shielded. You are even more exposed to the magnets that I apply to you. That's going to force you to go to the very downfield of the NMR spectrum. So you are less shielded. What are other reasons? So here is a table that you probably need to keep in mind. That whenever you need to check, do I have this functional group or not? You go to this table and trying to figure out, I see a peak in the range of 9 to 10. This might be an aldehyde. More electrons, that means more shielded. Then why would the double bond be more downfield, which usually fall in the range of those, than the single bond, which usually fall in the range of 0 to 1. So why is that happening? If you have benzene, for example, this range. This is the plane of the paper. The pink hydrogen we're circled here is here, okay? You're going to see each p orbital. When you have a bunch of p orbitals, it's going to form electrons like this. Those electrons, they're going to transfer between the single bond and the double bond. Just a quick recall from our discussion 1 when we draw resonance. I told you that those electrons will actually running all the way through the ring, that you cannot differentiate which of those two are making double bond. I'm making a running electrons like that in our benzene ring. Go back to our logic. What would happen when you have a moving electrons in your compound? It's going to generate magnet. There is another extra B1. Go through the electrons here. If I'm going to increase the B naught, there is going to have a higher energy gap. There's an extra B1 that is forming by the p orbitals of the benzene ring and pushing the benzene hydrogen to the range of 7 to 8. Okay, similarly, I draw another structure here. I just told you that it's aromatic. It's also going to have a B1 pointing up, and there's a extra B1 pointing down. So which is outside or inside of the ring. Just have a guess on what is going to be the reading of the proton inside, which is black, and outside. I'll give you 5 seconds to guess. I'm just going to tell you the answer. The hydrogen outside have a shift around 8-9, and the hydrogen inside actually is going to be negative 1.8. That's a negative number. For whoever is asking that question, are you talking about here? Which one is shielded, right? So when you see there are a bunch of electrons, that's shielded. See, shielded. I hope that answers your question. So next thing that you should pay attention to would be the shape of the peak. If it's CH, which means if the proton is bonded to carbon, usually it will have a very sharp peak like this. And whenever you see a peak of forward short peak like this, it's usually a hydroxyl group or it's bonded to a nitrogen. Table on discussion menu, you don't need to memorize. One thing that you probably need to pay attention to, enantiotopic protons or diastereotopic protons. The most useful example would be what happens to the proton here. Is my blue hydrogen and green hydrogen the same peak or not? We are going to talk about chemical equivalence first. The real exercise of today's discussion is, would you be able to identify if those hydrogens are in the same chemical environment? The similar words would be, are they chemical equivalents? Do those protons have the same chemical environment? Those kind of questions, they're all asking about the same. A quick look at the practice, which is usually our expectation. How many signals would you expect to see? The way to do that is when 3 hydrogens, so here there are 3 hydrogen, right? there are 3 hydrogens bonding to that carbon. The hydrogen bonding to the same carbon, usually they would have the same peak. If you can tell here, these 2 pairs of hydrogen, all those 6 blue hydrogen, they are all bonding to carbon, and then carbon, these 2 carbon are all bond to this green carbon. These 6 hydrogens have the same chemical environment. We call this chemical equivalence. This is the second signal because this hydrogen is bonded. It has a different chemical environment than those blue hydrogens. So this is the second kind of hydrogen. Here there is another 2, and we talk about anisotropic or diastereotropic. If it's not in the ring, and we talk about if those 2 hydrogens are bonded to the same carbon, then they are in the same chemical environment. So this is the third different kind of peaks that we are expecting to see in this compound. This is the 4th, 5th, 6th, and 7th. So there are totally 7 different signals because there are 7 different chemical environments. So here, 3 hydrogen. Here, there are 2 hydrogen. The hydrogen in the same color, they are chemical equivalents. So there is a hidden hydrogen, and this hidden hydrogen is actually a dash one. The 3rd, 4th, 5th, and this is the 6th, 7th. So there are totally 7 different hydrogen environments in this compound. Now we start to see symmetrical. So this one is symmetrical, which is going to show a little bit different. 3 hydrogen here. But on this side, these 3 hydrogen are going to behave similarly. So which means all the purple hydrogen in the compound that I'm showing here is going to show the same peak. These 2 hydrogen are going to behave similarly to these 2 hydrogens on the right. So that's second groups of electrons. Here is a hiding hydrogen. The hydrogen on hydroxyl group is going to be the 4th hydrogen. I hope this is not too hard. We talk about these 2 is going to be 2 different signals. And I'm actually going to use a model to explain why. Keep in mind that if you are forming a ring, and there is always going to be electrons around the ring, although it's not p orbitals, but there is some electrons, right? Look clearly at what those 2 hydrogen would behave. So I use a white one and a black one. Could you tell that they're in a different position of those magnets? So even just from this perspective, you can tell that these 2 is going to behave differently because they are in a different position. So I hope this is a better perspective. You need to understand that the reason that these 2 hydrogen is going to have 2 different peaks is they are diastereotropic. And you can, whenever you see a ring like this, you are going to have a very obvious idea that these 2 hydrogens are not going to be the same peak, although they are bonded to the same carbon. I'm still going to use different colors for different hydrogens. The wedge up hydrogen, the green hydrogen, these 2 are going to have the same peak. While the dash in hydrogen, the both dash in hydrogens is going to have the same peak. Here, there is a wedge out hydrogen, dash in hydrogen. And the rest of them are just wedge out. There's a dashed in hydrogen. There are 3 hydrogen here, so CH3. This 3 hydrogen is going to have the same peak. 1, 2, 3, 4, 5, 6, 7. Okay, there are 7 groups of different peaks. Okay, that's the wedge out hydrogen and the dash in hydrogen. They are different. Okay, so whenever you see a ring like that, and here CD, wedge out hydrogen, dash in hydrogen, right? Maybe you should also pay attention to G and F, because previously we talked about if both these 2 carbon are bonded to the same carbon, they should be in the same chemical environment. But why this one is not? It has something to do with the hidden hydrogen here on a double bond. So previously, if it's single bond, so if this one is a single bond, then G and F would have the same peak. But if it's not, so just a quick recall: single bond we can free rotate okay? So if it's single bond, it can free rotate, right? So this blue hydrogen, this blue carbon, hydrogen on this blue carbon, and the hydrogen on this black carbon is going to behave similarly because my sigma bond between the brown carbon and the purple carbon can free rotate, okay? But if it's double bond, and we all know double bond cannot rotate unless you're breaking the pi bond, which means this one, the bond between the bond between brown carbon and the purple carbon is fixed. The distance between those the hydrogens on blue carbon and the hydrogens on this black carbon is going to have different distance between those electrons. So let's back to all on the page, which means could you see there are different distance between this one and so they're going to have different distance. We talk about everything is about magnets and also double bond. If you're going to see they have different distance between those electrons or protons, but protons still have electrons, right? They are going to behave differently. And that's why G and F, which is the hydrogens on double bond, although they might bounce to the same carbon, they're going to have different signals. Okay. I hope I make this one clear. So similarly, you can see here, E and F, they have different signals. Practice on that for 1 minute, and we will quickly go through them. So compound G should have 4 signals. So how do I know that? Because I found a symmetrical plane. Then I just need to count one side. The other side should be the same, okay? So there is a wedge out hydrogen, and we spend some time talk about stereotopic dash hydrogen. These two are different. And there is a hidden dash hydrogen and 3CH3, okay? So there are totally 4 signals. Compound H, this is the first one. The second one, these 2 hydrogens in the same chemical environment. This one is the third, fourth, fifth. These 2 are the same. Here is a hydrogen, and this is different from others. So this red CH3 is different from this black CH3 because they have different distance to this purple hydrogen. So let's count. How many do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are totally 9 different signals. Okay, so did I see any questions? Oh, nice. Compound K. This CH3, and this CH3 are having the same chemical environment. These two hydrogen, and these 2 hydrogen are having the same chemical environment. The carbon in the middle is already bonded to 4 different things, which means there are no hydrogen on this green carbon. So totally there are only 2 signals, which is the blue signal and the yellow signal. Compound L also have a symmetrical plane. I know if it's writing in this way that you might not be able to see, but can you tell that this one is different? Just imagine this purple, black, and white is in the same plane because sp2 is in the same plane. They are in the same plane, okay? Just imagine that. It's symmetrical. So I don't know how good it is from your perspective. So there is a symmetrical plane in the middle of the compound. So when I see that, I know I just need to count one side. So wedge hydrogen, dash hydrogen, wedge hydrogen, dash hydrogen. There is a hidden hydrogen here. I'm going to remove the symmetrical plane. And the last one is the hydrogen on carboxylic acid. So totally there are 6 signals. Okay, there's a question. So the double bond is the reason why acyl hydrogens have different environments in compound H. Do you mean this 8 and 9 for whoever asking this question? Matthew, okay, there is a double bond and a double bond cannot free rotate. If this is a single bond, so think about if this is a single bond, then just for now, imagine, let me just remove the rest of it, okay? Just imagine if the bonds that I'm pointing at is a single bond, then these two, the purple and the red one, can have free rotation. When they rotate, so keep in mind, whenever you have free rotations, you cannot differentiate which is which, as long as they are both hydrogens. NMR is also like taking photos. When you take photos, they take turns to take the position previously each one was in. So you cannot tell the difference between them if you can free rotate. But if it's double bond, then this one is fixed. Your hydrogen, your white hydrogen here cannot change into the position of this purple one. And if I have different compounds on both sides of this part, let's say whatever, then this two is going to have different distance. It's going to be in a different magnet, and their signals will be different. I know this is probably hard to understand, okay? So when it is double bond, for example, if I have something very electronegative here, this electronegative things is going to steal electrons from my hydrogen here more seriously than hydrogen here, okay? So it's probably just going to steal a little bit. Does that make more sense to you? If I'm just having a single bond, so if I'm just having a single bond, then these two, they are going to free rotate. Very electronegative compound, atom is going to steal the same amount of hydrogen from both blue hydrogen and yellow hydrogen. Circle the hydrogen in each of the above compounds that is most deshielded. Okay, deshielded means electrons being stolen away. I'll just leave this question to you to exercise maybe a little. So we don't have much time. I'm just going to do it. So here, this hydrogen is the most deshielded hydrogen because oxygen is very electronegative, but also not only because of that, this resonance, the resonance between here. So I'm going to draw the resonance. The resonance between is going to form a very strong, so this is a strong electron withdrawing group because of both resonance and induction. Induction is the way to describe because oxygen is very electronegative, so it's stealing the electrons away from the hydrogen. So keep in mind, whenever you are asking, so if both resonance and induction exist, when both of these exist, the major reason is always going to be resonance. So major reason. Here, because chloro is very electronegative, then it's going to steal away the electrons. So all the yellow hydrogen in this compound, they are very deshielded. Here, this blue hydrogen is most deshielded because of the carbonyl. This one, they were very similar to each other. If I have to choose one of them that is most deshielded, I would choose the blue one because it's a primary. And then the rest of them are either secondary or tertiary carbon. I didn't get the chance to use my notes. Maybe I will talk about that next week. I think she will definitely talk about at least one of the mechanisms, at least either SN1 or SN2 in tomorrow's lecture. And it works better if you at least get in touch into some of them, and we will go through the notes part. Once Professor Levens started to talk about the mechanism of either substitution or elimination, and we are going to use the notes, it's going to be very helpful. Trust me. Okay, so that's the end of today's discussion. Bye-bye. Bye-bye.